So this video discusses some particular forces and also how to apply Newton's second law in different situations. So in the video of kinematics, we have seen how objects in free fall near the surface of the Earth have a gravitational acceleration of magnitude of 9.8 meter per second square that is directed towards the center of the Earth. And it was denoted by G. So using Newton's second law, we can calculate the force that caused this acceleration. So if the object has a mass m, then this force is equal to mg, and it is known as the weight of the object, okay? So the weight of an object is defined as the gravitational force exerted on the object by the Earth or any other astronomical body. For example, on another planet, G, the value of G would be different. So in a later video, we will see that a gravitational force exists between any two objects. But if one object is an astronomical body, such as the Earth, and the other is relatively smaller in size and mass, then the gravitational force in that case is known as the weight of the object. Also, you will see later that the gravitational force varies with the distance between two objects, okay? And so the value of G becomes less at higher altitudes. But near the surface of the Earth, we can assume that it has a constant value of 9.8 meter per second square. So this shows a person standing at the surface of the Earth. So there is the weight of the person, the gravitational force exerted on him or her by the Earth, and it is balanced by the upward normal force. Okay, and in this case, there's an object that is falling near the surface of the Earth, and the weight is the force that is acting on that object. So because weight is a gravitational force that varies with the distance between two objects, weight is not an intrinsic property of an object like mass, okay? So one common way to measure mass in everyday life is by measuring the weight of an object. So mass is equal to the weight divided by the gravitational acceleration g. So the term weight is usually misused to indicate the mass of an object. But as you can see, the two quantities are different. So mass is measured in kilograms and weight is a force that has the unit of Newton. So when we stand on a weighing scale, it would measure the downward gravitational force on us by the Earth or our weight, and then it would divide that value by g and display the mass in kilograms. So another common force in solving problems is the normal force. So when an object is in contact with a surface, either at rest or moving on it, then the surface will exert a supporting force on the object that is always perpendicular or normal to the surface of contact. So this force is known as the normal force N, and it can have any value depending on the configuration of the system, okay? So let's consider this example of a block that is resting on a surface, so the acceleration is 0, and if we apply Newton's second law, sigma f is equal ma equal to 0, then we have the resultant force is N minus W. So the normal force in this case is equal to the weight of the object. I'd note here that the weight and the normal force are not an action-reaction pair because action and reaction forces always act on different objects, so they can't cancel each other out. So you see here that the weight is cancelled by the normal force, right? So the reaction to the weight is the force that the block exerts on the Earth, okay? And the reaction to the normal force N is the force exerted by the block on the surface. So another important force is tension. So let's suppose an object is attached to a rope or a string. Then the rope will exert a force T on the object directed along the rope away from the object. And in solving problems, the mass of the rope is usually ignored, referred to as a light rope, and it is usually assumed to be unstretchable, okay? So in the case of a light rope, the magnitude of the tension force T would be the same at all points along the rope. So as the case with the normal force, the tension T can take any value depending on the configuration of the system. But let's take this example of a block hanging from the ceiling, okay, by a light rope. So since this block is at rest, its acceleration is zero, and if we apply Newton's second law, we get that the tension in the rope is equal to the weight of the object. So now let's consider the force of friction. So friction plays a very important role in our everyday life, right? So imagine that everything is very slippery, that even simple activities such as walking, sitting, holding an object, or driving a car would become extremely difficult or impossible. So the frictional force is a result of the interaction between the surface atoms of any two objects in contact, okay? And the direction of this force is opposite to the motion or planned motion of one object relative to the other. And so the normal force and the frictional force are both contact forces, and they are always perpendicular to each other. So let's consider a block resting on a surface. So suppose you try to pull this block to the right with an applied force, and suppose it remains at rest. Then this is because the applied force is balanced by an equal and opposite force. And this opposing force is known as the statistical frictional force, Fs. So it's statistical because it refers to the frictional force acting on an object when that object is still at rest, okay? And it has the value of Fs is equal to F. And so this statistical frictional force will increase as F will increase. So here we have F is increased and the statistical force will increase by an equal amount. But if f is increased to a certain maximum value, then the block will eventually start to accelerate and move to the right, okay? And this maximum value of the applied force F just before the block starts moving is given by F equal Fs max. So it represents the force when the block is at the verge of moving, okay? So it is the minimum force necessary to initiate motion. And when the block starts moving, the opposing frictional force is then known as the kinetic frictional force. So the kinetic frictional force is usually less than Fs max. So if Fk is equal to the applied force, then the block would move with a constant speed because the net force on it would be zero, right? And it would have no acceleration. But if F applied is less than Fk, or if F is removed, then the block will decelerate and will eventually come to rest. So experiments show that Fs and Fk have the following properties. So Fs max is equal to mu Sn, where mu s is the coefficient of static friction and n is the normal force acting on the block. And as long as the block is at rest, then Fs will be equal to F. So as F increase, Fs also will increase, okay? And Fs is always less than or equal to Fs max. And for the directions of Fs and Fk, they are always parallel to the surface. Fs is opposite to the component of the applied force that is parallel to the surface. So if this applied force is at some angle, then Fs would be opposite to the component of F applied that is parallel to the surface, okay? And the direction of Fk is opposite to the instantaneous velocity of the object relative to the surface. So mu k and mu s are dimensionless coefficients and they depend on the nature of the surfaces in contact. So mu k is generally less than mu s. And the table here, it shows different values of mu s and mu k for some materials. For example, for glass on glass, mu s is equal to 0.94 and mu k is 0.4. Also, mu k may vary with speed, but this is not included here. So friction is a complex phenomena, and one reason behind this is that the actual area of contact viewed from a microscopic level is much less than the area of contact from a macroscopic level. So as you can see here, okay, even for very smooth surfaces. So one peak would physically obstruct the other. Also, chemical bonds would continuously form and break between the atoms of the two surfaces. So there are many factors that can generate this overall force of friction. So another type of frictional force is the resistive force experienced by an object in relative motion to a fluid such as gas or liquid, okay? And the direction of this force is opposite to the direction of the object's velocity relative to the fluid. So you can feel this force if you put your hand out of the window of a fast-moving car. So the magnitude of the resistive force generally increases with the object speed, but can also have a complex dependence on speed, okay? So let's consider the case in which a large object is moving at a high speed through air, such as a skydiver. So the resistive force in this case is known as air drag and can be approximated to be proportional to the square of the speed. So rho is the density of air, A is the effective cross-sectional area, and C is the drag coefficient. And there is also an upward buoyant force that we neglect here, okay? So because the object speed is increasing due to gravity, okay, the resistive force will continuously increase. So as you can see, it starts small, but then as the skydiver is falling, it continues to increase until it becomes equal to the skydiver's weight. So in this case, the skydiver's acceleration will become zero and he or she would fall with a constant velocity known as the terminal velocity. So to find this terminal velocity, we apply Newton's second law. So sigma f is equal to zero because the acceleration is zero, right? And so the drag force is equal to the weight, and the terminal velocity is given by this equation. So as you can see, this shows why when the skydiver spread their arms and legs, their cross-sectional area A would increase, and this will decrease the terminal velocity. So let's consider now how to apply Newton's second law to solve problems. So it is necessary to follow some steps, which include to draw a free body diagram of each object in the system. So in a free body diagram, we consider the object as a particle and place it at the origin of a coordinate system, okay? So an object can be treated as a particle if all parts of the object move in exactly the same way. So if different parts of the object does not move in the same way, then Newton's second law is applied to the center of mass of the object, okay? Which is what will be represented in that case as the dot at the origin of the coordinate system. And we will consider the center of mass in another video. So usually in applying Newton's second law, the mass and friction of any rope or pulley are neglected, okay? So the second point in drawing a free body diagram of the object is to include all forces acting on the object, okay? So this is the, let's say the coordinate system. The object is at the center as a dot and you have to show each force acting on the object. And then you can apply Newton's second law along each axis using the components of each force, okay? So to simplify a problem, a coordinate system must be oriented in such a way that some forces are directed along some of the axes. And we will show this in the next slide. So let's consider this example. So suppose that a 25 kilogram block is released from rest at the top of an inclined rough surface. So rough means that there is friction, okay? And suppose that it accelerates downward in this direction at a rate of 0.1 meter per second square. And we want to find the coefficient of kinetic friction between the block and the surface, okay? So this figure here shows the free body diagram of the block, and as you can see, this block is represented as a dot here at the center of this coordinate system. And as you can see, all forces acting on the block are shown. So this is the weight of the block, the frictional force, and the normal force. And as you can see, for convenience, we oriented the x-axis along the slope. And so there are two forces along the axis. So only the weight that we need to use the component of to apply Newton's second law. So now we can apply Newton's second law in each direction, okay? So sigma fx is equal to max. And so mg sine theta here, because the component of the weight along the x-axis is equal to mg sine theta, okay? Minus fk is equal to ma. And n minus mg cosine theta is equal to 0 because there is no acceleration along the y-axis. So if we substitute for the mass, the angle, and also the acceleration, we get the kinetic frictional force is equal to 155 newtons, and the normal force is equal to 187.7 newtons, okay? And from this, we can find the coefficient of kinetic friction, and it is equal to 0.82. So let's now consider another example. So suppose that two masses m1 and m2 are connected by a massless rope that passes over a massless pulley. And we want to find the acceleration of the system and the tension in the rope. So as you can see, we first draw a free body diagram for each object in the system, showing all forces acting on each object, okay? So in this case, we only have the tension in the rope acting upwards and the weight downwards. And then we apply Newton's second law to each block. So because the two blocks are connected by a rope, they will have the same acceleration, and it is directed downwards for m2 and upwards for m1. And so we apply Newton's second law in the y direction for each block, and we get the acceleration and the tension in the rope. So now let's consider the example of uniform circular motion and how to apply Newton's second law in this case. So in the video of kinematics, we found that a particle moving in a circle with a constant linear speed, so uniform circular motion, has a centripetal acceleration directed towards the center of the circle and was given by v square over r. So r here is the radius of the circle. So this figure shows an object attached to a string in uniform circular motion, and the plane of motion here is parallel to the Earth's surface. So from Newton's second law, the centripetal acceleration is caused by a force or net force directed towards the center of the circle, okay? And so as a radial, the centripetal or radial force has a constant magnitude, but its direction is changing continuously. And if at some instant the radial force becomes zero, for example, let's suppose the string is cut, then the object would then move along a straight line path tangent to the circle. And so the centripetal force is necessary to keep the object in its circular path, okay? And this centripetal force may be any kind of force, such as friction, gravity, or tension. So let's consider the example of a conical pendulum, and it consists of a mass attached to a light string, and the mass is rotating in a horizontal circle, okay? And so we draw the free body diagram of this mass. So it is at the center of the coordinate system, and there are only two forces, the tension in the rope and the weight of the mass, okay? So the horizontal component of the tension force is what supplies the centripetal force to keep the mass in its circular path, okay? And the vertical component of the tension is what balances the weight of the mass. And so if we apply Newton's second law in each of the x and y directions, so we have along the y direction t cosine theta minus mg is equal to 0 because there is no acceleration in that direction. And along the x direction, we have only one force, which is equal to t sine theta, and it is equal to the centripetal force that is keeping the mass in its circular path. So we get this equation, and from these two, we get the equation for the speed of the mass, which is constant, okay? So the velocity of the mass is constant in magnitude, but is changing its direction, okay, continuously. So as another example, let's consider a car that needs to turn on a road without skidding. So we want to find the maximum speed for which the car can take the curved path safely. So in this case, the centripetal force required for the car to remain in its circular path is provided by the force of static friction, okay? And the maximum speed for which the car can take the curve without skidding is when the statistical frictional force is maximum, okay? So mu mg, the maximum statistical force, is equal to m v max square over r, and this gives the maximum speed for the car to take the turn. So now let's consider the example of a road that is banked, okay? So we want to find in this case the maximum speed for the car in which it can take the curved path safely without depending on friction. So in this case, when the road is banked, the car can take the turn without depending on friction as the required centripetal force. Because in this case, the horizontal component of the normal force is what supplies the necessary centripetal force. And so if we apply Newton's second law along the x direction, we get n sine theta is equal to mv square over r. And along the y direction, n cosine theta is equal to mg. And if we divide these two equations, we get this equation. So if the angle and the curvature r are known, then the safe speed limit for the car to take the turn can be found. And if the car moves at a speed lower or higher than that speed limit, then the frictional force must supply the additional centripetal force for the car to stay in its circular path. So let's consider this example. So in the video of kinematics of circular motion, we have shown that non-uniform circular motion has both a perpendicular and a parallel component of acceleration, okay? The perpendicular component is the centripetal radial acceleration, and this is the tangential component of acceleration due to the change in the magnitude of the velocity. So this is due to the change in the direction of the velocity, and the resultant component is given by this equation, okay? So these two accelerations are caused by the radial and tangential forces, okay? So we multiply the acceleration by the mass, and we get the resultant force acting on the object. So this figure shows the radial and tangential components acting on an object that is in non-uniform circular motion. So the radial component is what keeping the object in its circular path, and the tangential component is what changing the speed of the object, okay? So let's consider this example of an object attached to a light string and is rotating in a vertical circle of radius r, and we want to find the tension in the cord at the lowest and the highest point of the path. So let's apply Newton's second law along the tangential and radial directions. So along this tangential direction, the only force is this component of the weight, and it is equal to mat. So this component is what provides the tangential force that is changing the speed of the object, okay? And along this radial direction, the resultant force is T minus mg cosine theta. So this resultant force is what provides the centripetal force required to keep the object in its circular path, okay? So it is equal to mv square over r. So at the bottom, theta is equal to 0, and so AT is equal to 0, and we get this equation for the tension. And at the top, theta is equal to 180 degrees, and so AT is equal to 0, and we get this expression for the tension at the top position. So thank you for watching. Please don't forget to like and subscribe, and see you in the next